So what I'd like to do in this video is I'd like to talk to you about the Population Growth Lab. And so the first thing I'm going to do is I'm going to show you what I think is the easiest way to get to that lab. So you can get to it, through your course content, or you can actually go here and you can click on the module. And it actually has, for some of the modules, I've actually been able to make study guides for them. Some don't have them, but if you need it, it's right here. And then we'll just go through. As you can see, there's useful tips about other labs. Here's a walkthrough for the previous lab, and here's the Population Growth Lab. You can see there's some questions I've answered from students that I put here. That way everybody gets access to them, and you don't have to wait for my response. It's already here. And then you can just click here and get the handout. I've made this into a Word document, and I will post this in this course resource newsletter, and I'll also post it in the class website. That way you have access to it, and you can just kind of enter your data in there instead of a PDF file. Okay, so this is a population growth lab. So what we're going to do is we're going to use beans to represent our population. So there is a type of population sampling experiment, I guess, that people do. Scientists do, that where they tag a large group of species that they're interested in studying, and then what they do is they tag those samples. And so in this case you're going to use lima beans, and the lima beans, you're going to get about 200 to 250 lima beans, and then you're going to tag, you're just going to remove a sample of beans. So kind of take a handful and get around 40. If you've got a little more than 40, a little less than 40, that's okay. And then the ones that you tag, you're going to mark on them. Okay, draw something on the with your permanent marker on the bean. They're saying drawing a line that circles the entire bean. You can, you can write whatever you want on, put your initials on them, whatever you want to do, but something that lets you know that those are the tagged beans. Okay, then you're going to put those beans back in your paper bag, basically with all the rest of the beans that you have, that 200 250 set of beans. And you're going to put them in there, and you're going to shake it up and spread them around. That way they're all kind of randomized. Okay, then you're going to make a data table like this one, and what I've done is I've gone ahead and I've made this an editable data table, so you'll be able to add your data in here. Okay, and we'll do some practice for it. Okay, and then you're gonna put all your beans back in here, and then you're going to reach in the bag and pull out some beans. Okay, when you pull them out, you're going to spread them out on your table or wherever you're at, and you're going to say how many beans were tagged in that sample and how many total beans did you grab out. So in your handful, this is an example for sample 1. They had 29 beans that they pulled out of the bag, and 6 of those beans were tagged. Okay, so then we want to find out the percent tagged in that sample. Okay, so to do that, we're going to do some math. So we can do equals, and we're going to do 6 divided by 29. And then we're going to multiply that by 100. Okay, so 6 divided by 29, let me do this on my calculator. 6 divided by 29 is 0.206. Well, 2069. Okay, and then when we multiply that by 100, here, let me write it like this. I think it will make more sense if we write it like this. And I'll just move this chart a little bit. That way we've got more room here. So when I multiply that by 100, we're going to get 20.69. So that's the percent of beans. Okay, so you can do the same thing for this next one. Okay, they did this a second time. They shook it, they put those 29 beans back in, they shook the bag around, and then they grabbed out some more beans. This one they happened to get 33 beans out, and 8 of those 33 beans were tagged. So that ended up being 0.2424, and then they multiplied that, and you multiply it by 100, and you'll get 24.24%. Okay, then you'll do the next one, same thing, same thing, same thing, until you've done this 20 times. Okay, then once you've done that, you're going to do the average percent tagged. Okay, so you're going to add up everything in your sample, in this percent tag sample, so you'll be the sum. Let me see if I can find that symbol. Let me see if I can find it. I'm going to pause the video so okay, so it'll be the sum of the percent tagged in sample if you want to do it all at once, you can do it like this, and we're going to divide it by 20, and that'll give you your average percent tagged. Okay, and so that's part one. Okay, part two says population growth often has this exponential growth population. So we're going to practice again. Okay, we're still going to use our beans, but in this case we're going to use some pennies and some plastic cups and some markers, and still the marker. Okay, so we're going to label one cup the bean pot and another cup parents and the last cup offspring, and we're going to put 10 beans in the parent cup and the remaining beans in the bean pot cup. Okay, then we're going to create a data table. Okay, so here it is right here, and we want to take 2 pennies and we want to toss them in the air. The results of the toss will determine what happens. So if it's heads and heads, you're going to do nothing with the beans, you'll just do it again. If you have tails and tails, one parent will die, so we're going to take a bean from the parent cup and put it in the bean pot. And if you get heads and tails, you're going to have a baby, and you'll put something from the bean pot. We'll take a bean from the bean pot and put it in the parent cup. And then we'll take a bean from the bean pot and a bean from the parent cup and put both of those in the offspring cup. We're going to continue tossing pennies until there's no more beans in the parent cup. Okay. Then we're going to count the number of beans in the offspring cup and record the data for generation 1. Okay, so that will be generation 1. Okay, any beans in the offspring cup for generation 2 are going to get moved back to the parent cup. Okay, so let's say for generation 1, you had, let's say, 15 beans. Okay, we're going to take those 15 beans and we're going to put them back in the parent cup. Okay, and we're going to start over again. Okay, and then we'll have data for 10 generations. Okay, then, so that'll be the first time. This will be like, we'll call this, ooh, that's not what I want. We'll call this one, we'll call this experiment 1. Okay, then we're going to do this again. Okay, so I'm going to take this data table and I'm going to make a new one, and I'm going to call this experiment 2, and this one has social parameters. And we'll call this one no social parameters. Okay, so in experiment 2, you're going to do the same thing, but it's going to be just a little bit different. Okay, so if you have heads and heads, you'll do nothing with the beans, you'll just toss them again. If you have tails and tails, one parent in the population will die. We'll take a bean from the parent cup, put it in the bean pot. If you have heads and tails, and this means the penny that has heads is the left penny, and then the tails will be on the right. The parents will have a baby, and we'll take a bean from the bean pot and we'll put the bean and the parent in the offspring cup. And then if you have tails and heads, which means the tails penny is on the left, the parents will not have a baby. And so we're going to take a bean from the parent cup and put it in the offspring cup. Okay, and so we'll do this again. You know, we might have 12 here. And we'll go all the way down. Okay? And those will be your 2 experiments. Okay? Now that you've gotten your data, you should have this data table full and this data table full and this data table full. Okay, now that you've done that, we can do the analysis and discussion section. And this is what will be in the analysis and discussion section of your lab report. Okay, we're going to use some statistics to predict the population size from your tagged population sampling. Okay, so we want to expect the sample population percent of tagged beans would be similar to the true percentage of tagged beans in the total population. So we're going to calculate the mean of the 20 percentages. Okay, so to do that, we're going to take the number originally tagged and then the mean of the 20 sample percentages. Okay, so let's see. Okay, so what we're going to do is we've got, you know, something here. Let's say our average was like 7 beans. Let's try that, okay? Just as an example. Okay? So we'll have X here. Let me do this in red. And then you originally had what, like 43? And we'll divide that by mean of the 20 sample percentages. So let's just say we have 20.69 and 24. Let's just say it's 22%. Okay, I'm just guessing. So now we can do our math, right? And then we'll have derp. We can just do let's see, 43 divided by 0.22. Let's see what that is. Okay, that gives us 195. Okay, so this is our estimated population size, or calculated population size. Okay, so now that you've done this, you can actually take your actual population size and you can get your percent error. Okay, and so in order to do that, you'll do your percent error is going to be like, you're going to take your estimated you're going to do that over your actual and then you're going to put an X here. You'll put a 100 here. Okay, and then you'll just, you'll solve for X. Okay, so let's see if we can do that. I'm going to do kind of the algebra for you. That way it'll be a little bit easier for you. Estimated population size. And see, I don't know what these real numbers are, so you're just going to need to if your estimated is actually higher than your actual population size, you may get you know, you may get a number, you may get a number more than 100, and then like however much more that is over 100 would be your your percent difference. So we'll do an example. Okay. Okay, so that's how you would get X. Now let's pretend. So we had our estimated population size, and I'll show you what I mean by being bigger. Okay, let's say it's 195 was our estimated, and our actual was 190. Okay, so we'll have 195 times 100 divided by 190. Okay, so let me put that in my calculator. So I'm going to get 102.63%. Okay, so that means it's 2.63% more. So our actual like percent error, here, let me see. This should actually go here. Your percent error is going to be right here. Okay, so the percent error is actually 102.63 minus 100, which is 2.63. Okay, that's how much it's off. Okay, the same kind of thing, if you get like, you know, 98, then you would do 100 minus 98 equals 2%. Okay, so that would be your percent error. Okay, that's just an example. Okay, so what's going to cause our results to be off from the actual population? You'll answer this question in your analysis section. Okay. How might the sample size and the population affect your findings? How might the number of random samples collected influence your findings? Again, you're going to answer this in your analysis section. What concerns should a biologist have about a species habitat before we use this method to approximate the size of a population? Again, you're going to answer that in the analysis section. Now, we're going to prepare a graph of our population growth for each set of social parameters. And so we're going to use the generation number on the x-axis and the population size on the y-axis. Okay, so here's what I'm going to do. I'm going to put some fake data in here. Okay. Again, I'm totally making this up. I don't even know if this is going to show exponential, but we'll see how it goes. For this one, we'll do okay, so now I've put this in the data in Excel, and I just copied and pasted these charts into Excel, and I'm going to make my graphs. Okay, the first thing I'm going to do is I'm going to highlight these two. I'm going to see if it'll make it correctly right here. Okay, So we want generation number on the x-axis, which is what it did. Okay, but I need to label it. And then I'm going to do population size. And I'm going to call this one no social parameters. Okay, so I've got one graph, and now I'm going to make my second one. Okay. So let's see if I can get this to go up to 120. That way it looks the same as the other one. Okay, I just want them both to kind of look the same, because if they both go up to 120, then it's easier to compare the two. Okay, and I want to add the axes titles again. So this one is going to be generation number. This one's going to be population size. So you can see my numbers are made up. Your data is going to look a lot better because you're going to do the you're going to actually do the lab. I just kind of made it up. I just wanted to have some data to show you. Okay, so now I'm going to take this graph and I'm going to copy and paste it in here. I'm going to take this graph and copy and paste it in here. Okay, and then now we want to determine the doubling time for the population at the beginning, middle, and end of the graph. And then are they the same? Why or why not? So the middle, if you've got 10, right? So it would be like generation like 1, 5, and 10. Okay. And then for our doubling time, okay. So in order to get doubling time, there's a couple ways we can do it. You can look at your graph, and if your graph, let's see what we have here. Let me get my data table back. Okay, so the doubling time at population size 1 it'll be the time it takes to get to 30. Okay, and then for 5 it would be the time it takes to get to 81, and then for 10 it would be the time it takes to get to 220. So okay, now in order to calculate doubling time, we're going to have to do a couple of things. So here's what I'm going to do. First, we need to calculate the growth rate. And I'm going to do this in Excel just because it's going to be a little easier. And so our growth rate, we need to take our, remember, our original population size was 10, right? We had 10 in the parent bucket. So our growth rate, we are going to take our current size. Let me write this here. And then so I'm going to give you these graphs, right? I'm going to give you these formulas here. We'll do the current population size minus the original population size. And we're going to divide that by the original population size. Okay, that's how you get doubling time. And then in AP Environmental Science, we use something called the rule of 70 to calculate, this isn't going to give you doubling time. This is going to give you like the growth rate. which then we need for the rule of 70. Usually they give you the growth. They already have given you the growth rate. So the doubling time is equal to 70 divided by the growth rate. And you want to put the growth rate in as a whole number. And I'll explain how to do that. Okay? So that's how you do this part. So to calculate the growth rate, I'm going to do the current population size, which is 15. I'm going to do minus 10 divided by 10. Okay? And I'm going to do this the whole way down. Okay, there we go. Okay, now you can see it starts getting really big. Okay, then we do doubling time. Okay, for doubling time, we're going to do 70 divided by 50. Okay, because our growth rate is really 50. Okay, and that's going to be, usually if you have years, it'll be years, but for us, it's going to be generations because, you know, we don't have years. Okay, and so then this one would be 70 divided by 70, so that would be like in one generation, it'll double. And then we'll have 70 divided by 100. Okay, less than one generation. And you can see in a third of a generation, you can see it's going to start getting really, really big. Okay, and that's because, let me see if I can get this to work. Oh, no, that's not going to work. That's because this is an exponential growth, and so it's growing really, really fast. Okay, and we can do the same thing over here. Okay, our growth rate is going to be our current population size, which is 12, minus 10 divided by 10. Okay, and so we'll do that all the way down. And then, and these numbers again are going to look a little bit weird because, remember, I made them up. So this one, our growth rate is, remember, we used the rule of 70, so we did 70 divided by, this is 20%, and so we did 70 divided by 20, and that gave us 3.5. Okay, same thing we'll do here, 70 divided by 40, 70 divided by 80, 70 divided by 150. So if you need to, you can multiply it by 100 if that makes it easier for you. And that's what it means by putting the growth rate in as a whole number. You're basically putting like the growth percent instead of the growth like decimal. Okay, and then you want to know if the population doubling times for the beginning, middle, and end of the graph are the same. Okay, so here's the beginning one, right? Here's the middle. And then here's the end. Okay, obviously they're different, right? So let's look here. Same thing. Okay. And you're obviously going to do this with your data, not mine. Okay, I might have done this wrong. Yeah. Okay. Okay, so you can see that these are different. Okay. And the smaller the number is, the faster it will double. The population will double. The quicker it will double. Okay, it means like the fewer number of generations it takes to double. Okay, so that's what that means. The smaller the number, the faster the population is growing. So this would be like slow, fast, super fast. Okay. So we're going to assume that a generation is equal to 20 years. There we go. Okay. So we're going to use the doubling time from the graph to calculate the growth rate of the population, we're going to use the formula below. Okay, so this is the rule of 70 that we already did, basically. So we've already kind of done that. We just kind of did it backwards. And then you want to calculate the doubling time and the growth rate for the second set of data, just like you did with the first, and then compare the two. So you can see that, like, this one is slow, but this one's even slower. This one's fast. This one's not nearly as fast. Okay, you can see. And really, when you're doing this, your social parameter one should be a lot, you know, these numbers will be a lot smaller than these numbers. And so your data will be even more different. I didn't do a very good job of making up fake numbers. Okay, and then you're going to write a paragraph explaining why the world population is growing at the projected rate, what this means for the world's inhabitants, and what we do to address population growth. You can see here we have the rubric. This is the generic rubric. But if we actually go into your course, we can go into the Dropbox folder for this lab. And you can see the rubric right here. And this rubric is more specific to this lab. Okay, so it's saying like the data tables are included, the pictures of the lab is included, your graphs are included, all that kind of stuff. So this one is a little more specific to your lab if you want to see exactly specifically what you need. Okay, so then if you're writing a lab report, let's just go all the way with it. If you're writing a lab report, you'll put your name, and then you'll have your different sections. And this is actually how I would make my lab if I was you. This is how I would write my lab report. Okay, I would go ahead and I would just take this from the you know, the main area of the rubric, and I would just copy it here, and then you make sure that you've got all that stuff into your, you know, in your lab in that section. Okay. You know, and then you can just make sure you've got all of these parts, and you know, and then you'll know you definitely are getting full credit for this lab because you've included all of the required parts. Okay. And then you'll just, you know, fill it in, put your stuff in there where it goes. Like, so if your data tables, you'll put them in the data section. Your graphs, you'll put them, you know, instead of this, just put your graphs in here, right? So I'm going to take what I made, my graphs that I made, you know, and I'm going to plot my graph in right here. Now for your procedure, make sure you don't write the procedure word for word. You need to actually, from the lab, you need to kind of put it in your own words. Okay, you'll lose points if you don't put it in your own words. Okay, so data tables, right? There's my data table, okay? And so I'm kind of like building my lab report as I kind of go along, right? And that way I can make sure that I've got everything that I need in here. Okay. So anyway, hopefully that is a helpful for you for this lab. What I'm going to do is I'm going to take this Word document right here, and I'm going to save it, and I'm going to post it for you in the course so you can download it, and then you know, you can you can use it yourself and edit it. Just remember that these numbers that I made are not correct. So you're going to want to put your own numbers in here. I'll probably erase these before I give it to you, just so you can make sure that it's right. But I'll I'll keep all these numbers and stuff in here. Okay. And I'll I guess I can keep the graphs in here so you can kind of see what they're supposed to look like. So maybe I'll leave the data and then you can just replace with your own. And then, I'll leave this section too. This too, so you can, and I would have done this in a new document if I was you, but I was getting it ready to turn in, but I'll just leave this here so that way you can kind of see what you need to do. Okay. So hopefully this was useful.